Good evening. Uh, am I audible and is the screen visible?
Yes, you are audible and the screen is also visible.
Okay, thank you. I welcome all of you to the ninth live session of the course Thermodynamics, which is being offered by IIT Delhi. As in for myself, I am Abhik Dev, a PMRF PhD scholar in the Department of Mechanical Engineering at IIC Bangalore. And in this live sessions, I shall be helping you with the problem solving skills related to the concepts that were discussed in the previous week lecture of the course, so as to clear doubts related to the concepts and also help you with the solution of the problems related to the assignments. Uh, Today we shall be discussing on the concept of gas mixtures and gas vapor mixture. So in any of the uh, at any point of time, if there is any doubt, please do interrupt and ask me so that we can clear it right then. So without further delay, let us start with today's session. uh, okay, so first we will solve some of the problems related to gas mixtures, and then we will move to gas vapor mixture. So the first problem, consider a gas mixture that consists of 3 kg of oxygen and 5 kg of nitrogen and 12 kg of methane. Determine the mass fraction of each component, the mole fraction of each component, and the average molar mass and gas constant of the mixture. So I am quite certain that these probably was most of you have already solved this kinds of problem in class in your higher secondary exam, in your higher secondary course, so or in basic BTech course. So we will start with this very basic problem, and then we'll move on to some a little complicated ones. Okay, so uh, the total mass, so there is 3 kg of oxygen, 5 kg of nitrogen, and 12 kg of methane. So first we have to determine the mass fraction. We have to determine what is the total mass of the mixture. Okay, the total mass of the mixture is equal to 3 plus 5 plus 12, that is 20 kg. Okay, so the first one, that is the mass fraction of oxygen. So what is basically mass fraction? Mass fraction is the mass of a component divided by the total mass of the mixture. So mass fraction of oxygen will be uh, it is denoted, let us denote it as X subscript O2, and this will be the mass of O2 by the mass of the mixture. So here the total mass of the mixture is Pm. So this is 3 by 20, that is 0.15. So this is the mass fraction of oxygen. Similarly, for the other two, the mass fraction of nitrogen is equal to X of N2, that is mass of N2 by the total mass. So this is 5 by 20 is 0.25, and the mass fraction of methane CH4, mass of the CH4 by the total mass of the mixture. So this is 12 by 20, it is 0.60. So these are the mass fractions. So what are the mole fractions of each component? So for the mole fractions of each component, uh, we have to first determine what are the number of moles of each component that is present in the mixture. Okay, so number of moles of oxygen is equal to, let's say, N of O2, that is the mass. The number of moles is obviously the mass by the molecular mass. So it is 3 by 32. This is in kg. So this will be, we are taking it as kg per kilomole. So this will come out as 0.094 kilomole. Similarly, the number of moles
Battery is discharging.
nitrogen is N of nitrogen. This will be equal to 5 by 28, that is equal to 0.179 kilomole. And number of moles of methane, that is NCH4, this is equal to 12 by 16. So these are the molecular masses in kg per kilomole, and it comes out to be 0.750 kilomole. Okay, therefore total number of moles N is the sum of these three. So this is 1.023 kilomole. Therefore mole fraction of oxygen is 0.094 by 1.023. So mole fraction is the number of moles of oxygen by the total number of moles. So this is 0.092. Then the mole fraction of nitrogen is 0.179 by 1.023. So this is 0.175. And mole fraction of methane is equal to 0.750 by 1.03, that is 0.733. So we have found out what are the individual mole fractions. Now coming to the average molar mass. So average molar mass is equal to the total mass of the mixture by the total number of moles. It can be specified that way. So this is equal to the total mass of the mixture by total number of moles. So this is 20 is the total mass of the mixture, and the total number of moles we have found out to be 1.023. So this is 19.6 kg per kilo mole. Okay, and average gas constant of the mixture will be equal to the universal gas constant by the average molar mass that we have found out. So this is 8.314 by 19.6. So this is 0.424 kilojoule per kg Kelvin. Okay, so I hope it is clear to everybody. So if there is no doubt, then we will move on to the next problem. Okay, so let us move on to the next problem. So a gas mixture has the following composition in terms of mass fraction. Hydrogen is 0.10%, that is the mass fraction of hydrogen is 0.10, the mass fraction of nitrogen is 0.60, and the mass fraction of carbon dioxide is 0.30. Now determine the composition in terms of mole fractions and the apparent molecular weight of the mixture. So as we can see that the mass fractions of the gases are given, but the total mass of the mixture is not given. Okay, or any mass value is not given. So first we will assume the total mass of the mixture. So let us assume that the total mass of mixture be mkg. Okay, therefore the mass of hydrogen in the mixture will be 0.10 mkg. The mass of nitrogen will be 0.60 mkg, and the mass of carbon dioxide is 0.30 mkg. Okay, now we have to determine the composition in terms of the mole fractions first. So first we have to determine what are the moles, number of moles of each component. So the number of moles of hydrogen is this mass 0.10 m by the molecular mass of hydrogen, that is 2. Okay, similarly the number of moles of nitrogen is 0.60 m by 28 and number of moles of carbon dioxide is 0.30 m by 44. 44 is the molecular mass of carbon dioxide. Okay. Then from this number of moles, let us determine what is the total number of moles. Therefore, the total number of moles of the mixture, this is equal to 0.1 m by 2 plus 0.6 m by 28 plus 0.3 m by 44. So this is equal to 0.0782 m. Now therefore from this we can now determine what are the mole fractions. Therefore the mole fraction of hydrogen is equal to 0.1 m by 2. This is the number of, this was the number of moles of hydrogen, uh, and the total number of moles is 0.0782 m. So the m gets cancelled from both, from the numerator and denominator. So that is why we have taken a value m as an arbitrary value, so that we know that it will get cancelled ultimately. Okay, so this value comes out to be 0.6394. Okay, the mole fraction of nitrogen, that is 0.6 m by 28 divided by 0.0782, so m, so this comes out to be 0.2740, and mole fraction of carbon dioxide, that will be 0.3 m by 44 divided by 0.0782 m, and the value will be 0.0870. So we have determined what is the composition of the mixture, as asked, composition of the mixture in terms of the mole fractions. Okay. Now what is the apparent molecular weight of the mixture? The apparent molecular weight of the mixture, this is equal to the mass of the mixture by number of moles of the mixture. So we have taken the mass to be arbitrarily mkg. So and the number of moles in that consideration we have found out to be 0.0872 m. So 0.0872 m, and thus the molecular mass comes out to be 12.79 kg per kilomole. So it is interesting to note that even if the total mass or anything is not given, only with the mole fractions we can determine what is the molecular weight of the mixture and what is the what will be the composition of the mixture in terms of the mole fractions. Okay, so if there is any doubt you can ask, else we will move on to the next problem. Okay, so if there is no doubt, we will move on to the next problem. Here we will analyze mixture of gases based on the ideal gas equation of state, the K's rule, and the Amicuff's and Dalton's law applied along with compressibility. So I hope that in the theory classes, the K's rule and Amicuff's law and the Dalton's law have already been discussed. And ideal gas equation of state has been discussed since very long time. So let us start with with the application of these. Okay, so a rigid tank a rigid tank contains 2 kmol of nitrogen and 6 kmol of carbon dioxide gases at 300 Kelvin and 15 megapascal. Estimate the volume of the tank on the basis of the ideal gas equation of state, the K's rule, the compressibility factor and the Amicuff's law, and the compressibility factor and the Dalton's law. So what have we been provided with? There is a rigid tank that contains 2 kilomole of nitrogen and 6 kilomole of carbon dioxide at this temperature and this pressure. Okay, so first we will start with the ideal gas equation of state. So using ideal gas equation, the pressure of the mixture multiplied by the volume of the mixture is equal to the number of moles of the mixture. This is the molar specific volume of the mixture, number of moles of the mixture, the universal gas constant, and the temperature Tm. Okay, therefore, the volume of the mixture from this can be found out like Nm r universal Tm by Pm. Okay, so what is the total number of moles? Nm is equal to the total number of moles, and that is equal to 2 plus 6 equals to 8 kilomole. Okay, this is equal to 8 into, therefore 8.314, that is universal gas constant, multiplied by 300, and this is 15 10 to the power 3. We are keeping only 10 to the power 3 because 8.314 is also in kilojoule and this will be in kilopascal. So this comes out to be 1.330 meter cube. So this is the volume using the ideal gas equation of state. Now we will use the K's rule. So what does the K's rule state? So according to K's rule, uh, the critical temperature of the mixture will be equal to the sum of the product of the mole fraction of the component and the critical temperature. That is, if we take the product of the mole fraction of of each individual component and its individual critical temperature, and we sum up all these values for the mixture, then we'll get the critical temperature and critical pressure. Similarly, for the critical pressure of the mixture. So in this way, we can proceed with characterizing the mixture from the individual components. So how will we go about it? Uh, First, we have to determine what are the mole fractions of the mixtures. So by K's rule. Okay. So now the mole fraction of nitrogen, this is equal to y into is equal to 2 by 8, that is 0.25, and and mole fraction of carbon dioxide, that is YCO2, is 6 by 8, that is 0.75. Okay. Now we will call the critical temperature and critical pressure as these they will be obtained from the summation of the mass fraction, mole fraction, and the critical temperature and critical pressure of individual components. So we will call them as pseudo critical temperature and pseudo critical pressure of the mixture. So accordingly, uh, pseudo critical temperature of mixture T critical, let's denote it as T critical M, that will be the summation of this value. That is, if we first do a product of the mole fraction and the critical component, critical temperature of the individual components, and then sum it up for all the components, and we'll get the critical pseudo critical temperature of the mixture. So this is equal to Yn2 T critical N2 plus Y CO2 T critical CO2 will be in subscript. Okay, CO2. So we have determined the mole fractions to be 0.25 and 0.75. So 0.25 multiplied by, from the critical temperature of nitrogen, the critical temperature of nitrogen is 126.2, 126.2, plus this is 0.75, and the critical temperature of carbon dioxide is 304.2 Kelvin. So this will come out to be 259.7 Kelvin. Okay, and similarly for the critical pressure, pseudo critical pressure of mixture is PCRM, that is equal to YIPCRI. Similarly, same. So YN2 PCRN2 plus YCO2 PCrCO2. So that is 0.25 multiplied by 3.39 plus 0.75 multiplied by 7.39, and it comes out to be 6.39 ampere. Okay. Therefore, from this reduced pseudo-critical temperature and pressure of the mixture, we will now calculate the reduced temperature and reduced pressure of the mixture. Therefore, reduced temperature of mixture is equal to Tm by T critical M, that is 300 by 259.7 into 1.16, and reduced pressure of mixture PR, that is Pm by P critical M, 15 by 6.39, so that will be 2.35. Now corresponding to these values, we'll find out the compressibility corresponding to TR equals to 1.16 and PR is equal to 2.35. The compressibility Z for the mixture is 0.49. From the generalized compressibility chart you can find out. So therefore the volume in this case will be equal to the compressibility multiplied by the volume in as obtained from the ideal one. So this is 0.49 multiplied by 1.330. So this is 0.652 meter cube. Okay. So this is the volume of the mixture as obtained from the K's rule. I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so I am taking that there is no doubt. So we will move on to the next part of the problem, that is uh, using the compressibility factor and the Amagat's law. So using Amagat's law and compressibility factor. Okay, so what happens is that in this case, so now Zm for Amagat's law, the compressibility of the mixture is taken as the summation of the product of the mole fraction and the compressibility of the individual components, where this Zi, this compressibility of the individual components, is determined at the mixture temperature and mixture pressure for individual gases. Okay, so we know the temperature and the pressure of the mixture. So now for nitrogen we can determine what is the reduced temperature and reduced pressure for nitrogen. For nitrogen, the reduced temperature of nitrogen is the, we have to determine these values at the mixture temperature and mixture pressure. So mixture temperature divided by the critical temperature of nitrogen. Okay, so this mixture temperature is 300 and the critical temperature of nitrogen is 126.2. So this is 2.38. So the reduced temperature of nitrogen with respect to the mixture temperature is 2.38, and the reduced pressure of nitrogen, okay, for that can, this is a mixture pressure and the critical pressure of nitrogen. Okay, so the mixture pressure is 15 megapascal and the critical pressure of nitrogen is 3.39. So the value for compressible reduced pressure is 4.42. Okay, now corresponding to these values, corresponding to these two values, the compressibility of nitrogen from the compressibility chart is found to be 1.02. Okay, now for carbon dioxide, similarly we will determine the reduced temperature with respect to the melting temperature, mixture temperature, and divide it by the critical temperature of carbon dioxide here. So this is 300 by 304.2, that is equal to 0.99, and reduced pressure of carbon dioxide is mixture pressure by pressure of carbon dioxide, that is 15 by 7.39, so that is equal to 2.03. So corresponding to these two values, the compressibility comes out to be 0.30. Okay. Now, by Amagat's law, so we have already determined, corresponding to Amagat's law, the reduced temperature, reduced pressure for the individual components. Now we will use these compressibilities to determine the compressibility of the mixture. So Zm is summation of Yi Zi. So this is 0.25 multiplied by 1.02 plus 0.75 multiplied by 0.30, and this value comes out to be 0.48. Okay. Therefore, the volume of the mixture as per the Amagat's law and using compressibility will be this compressibility multiplied by the ideal, the volume that we obtained from the ideal gas equation. So this is 0.48 multiplied by 1.330, that is equal to 0.638 meter cube. So I hope this is clear to everybody. If there is any doubt, you can ask. So I am taking that there is no doubt. So I will move on to the next part of the problem. And now we will use the same thing. I mean, for the same problem, we will use the Dalton's law and the compressibility. Now, Z for the mixture for Dalton's law is given as summation of Yi Zi. This is similar to the Amagat's law, but here Zi is evaluated at is evaluated at Tm and Vm for individual gases. So earlier it was for Tm and the pressure of the mixture, but now it is the volume of the mixture. But the volume of the mixture, mm, volume of the mixture we is not known to us. So how will we go about it? So we will this Vm, okay. So we will use the pseudo reduced since Vm is not known to us, we will assume the initial volume to be the one that we obtain from the ideal gas equation. Okay, and accordingly we will calculate the pseudo reduced volume. Okay, so okay, we assume Vm equals to Vm ideal. Okay, and we calculate the pseudo reduced volume as this is equal to mm, this is Vm ideal that we have taken and divided by the universal gas constant, the critical temperature of nitrogen, the number of moles of nitrogen, and the critical pressure of nitrogen. So this is called the pseudo reduced volume. Okay, so the pseudo reduced volume for this comes out to be 8.314, this is 1.330 divided by 8.314 multiplied by 126.2, this is the number of moles of nitrogen was 2. um, 3390. Okay, so this comes out to be 2.15. And the similarly so this is like V okay, so this is a pseudo reduced volume, and so let us denote it as BR N2. Similarly, the pseudo reduced volume for carbon dioxide, that is BrCO2, that will be same Vm ideal by the universal gas constant, the critical temperature of carbon dioxide, number of moles of carbon dioxide, and the critical pressure of carbon dioxide. So this is 1.330 divided by 8.314 multiplied by 304.2 multiplied by 6 divided by 7390. So this is 0.648. Okay. From this uh, reduced volume, now we will determine from the just like in the Amagat's law, the reduced temperature values will be the same. So the reduced temperature of nitrogen will be 300 by 126.2, that is 2.38, and the reduced temperature for carbon dioxide is 300 by 304.2, that is 0.99. So corresponding to these values, we will now determine the compressibilities. So for nitrogen, corresponding to TR equals to 2.38, and the reduced pressure value of reduced pseudo reduced volume value of 2.15, we can determine from the generalized compressibility chart the compressibility of factor for nitrogen to be 0.99, and for carbon dioxide, corresponding to the reduced temperature value of 0.99 and the pseudo reduced volume value of 0.648, the compressibility of carbon dioxide comes out to be 0.56. Okay. So now by Dalton's law, uh, what happens is we can just like Amagat's law, the compressibility of the mixture will be the sum of the product of the mole fraction and the individual uh, compressibility values. So by Dalton's law, the compressibility of the mixture is this summation of yi zi. So 0.25 multiplied by z for nitrogen is 0.99, and the compressibility for the mole fraction of carbon dioxide is 0.75 multiplied by the compressibility of carbon dioxide is 0.56. So this compressibility of the mixture comes out to be 0.67. Accordingly, the volume of the mixture from this Dalton's law and the compressibility will be equal to this compressibility factor that we have determined using this multiplied by the volume in the that was obtained from the ideal gas equation. So this is 0.67 multiplied by 1.330, that is equal to 0.891 meter cube. So basically we can see how it changes from one consideration to another. Using the ideal gas equation, the volume was 1.330 meter cube. By using the K's rule, the volume of the mixture came to be 0.652 meter cube. Using the Amagat's law in conjunction with the compressibility factor, the volume came out to be 0.638 meter cube. And using the Dalton's law and in conjunction with compressibility, the volume came out to be 0.891 meter cube. So like different processes, different considerations are giving us different value of the volume in case of mixture. Now if there is any doubt, you can ask, else we will move on to the next problem. Okay, so I am taking that there is no doubt. So we will move on to the next problem. So this is like mm, uh, a tank with a partition with different gases in each of the partition, and then they are mixed. So we have to determine what is the temperature and pressure of the mixture. So what have we been supplied with? An insulated rigid tank is divided into two compartments by a partition. One compartment contains 7 kg of oxygen gas at 40 degrees Celsius and 100 kilopascal, and the other compartment contains 4 kg of nitrogen gas at 20 degrees Celsius and 150 kilopascal. Now the partition is removed and the two gases are allowed to mix with each other. Now determine the mixture temperature and the mixture pressure after the equilibrium has been established. Okay, so let us first start with the description of the problem that we have been given. So this is the rigid tank. Okay, there is oxygen in one, 7 kg at 40 degrees Celsius and 100 kPa, and in the other compartment there is nitrogen or 4 kg mass at 20 degrees Celsius and 150 kPa. Okay, now we are now assuming that both the gases are behaving as an ideal gas. So this is a first assumption that both oxygen and nitrogen behave as ideal gas. Okay, now from the energy balance, so this is a closed system, right? There is no mass that is crossing the boundary, so we can consider it as a system analysis rather than a control volume analysis. So if we consider the energy balance of this system, a system that is consisting of the mass inside the entire tank, so from the energy balance, so from energy balance, so from energy balance, delta E of the system, that is E in minus E out, that will be 0. There is no change in the energy of the system. Okay, so if we neglect the changes in the kinetic energy and the potential energy, then the change in the internal energy of the system will be 0 by neglecting changes in kinetic energy and potential energy. Okay, so if the change in internal energy is 0, then we can write it as mcv. T is the, let us consider that the mixture temperature, that is after the mixing of the two gases, the temperature becomes Tm, that is at equilibrium temperature of the mixture is Tm. So Tm minus the initial temperature of the gas. So these values for oxygen plus the same these values for nitrogen, where this Tm is mixture temperature. Okay, so let us put in the values. Now for nitrogen, this specific heat and constant volume is 0.743 kilojoule per kg Kelvin. So these values can be easily obtained from any property standard property table for nitrogen, and similarly for oxygen. And for oxygen, the CV value is 0.658, kilojoule per kg Kelvin. So this 4, if we put in the values, then it is 4 into 0.743 into Tm minus 20. Here we are not converting it to Kelvin because the temperature difference in degrees Celsius and temperature difference in Kelvin will give the same value. So we are just putting the values directly. So this is 7 multiplied by 0.658 divided by Tm minus 40. So from this, by solving this, we get the value of Tm to be 32.2 degrees Celsius. Therefore, the mixture temperature is 32.2 degrees Celsius. 32.2 degrees Celsius. Okay. Now, what do we need to determine? The mixture pressure after the equilibrium is established. So, for pressure, let us we have the this uh, number of moles of oxygen will be this mass of oxygen by the mass of oxygen. So, the mass of oxygen is 7 kg and the mass of nitrogen is 4 kg. So this is 7 by molecular mass of oxygen is 32. So the number of moles is 0.219 kilomole. Okay, and the number of moles of nitrogen is the same, the mass of nitrogen by molecular mass of nitrogen. So the mass of nitrogen is 4 kg and the molecular mass of nitrogen is 28. So this value comes out to be 0.143 kilomole. Okay, now therefore the total number of moles in the mixture that is Nm is number of moles of oxygen plus number of moles of nitrogen divided by that is 0.219 plus 0.143 that is 0.362 kilomole. Okay, now using the ideal gas equation, so we now have the total number of moles of the mixture. The mixture temperature we have already determined to be 32.2 degrees Celsius. So the mixture temperature is 32.2 degrees Celsius, or that is 305.2 Kelvin. So for determining the pressure, final pressure of the mixture, we have to determine what will be the volume of the final mixture. So a very important consideration here is that the tank is rigid. Since the tank is rigid, so initially say the volume of the oxygen was V1 and the volume of nitrogen was volume of oxygen was VO2 and volume of nitrogen was VN2. Then since the mixture is since the tank is rigid, so after mixing, the total volume will remain the same. That is, initially the total volume was V1 plus V2, and finally also the total volume will be V1 plus V2, and that will be equal to the volume of the mixture. So we can determine the volume of the mixture as by determining first the individual volumes of the gases. So from the ideal gas equation, now the volume of oxygen is the number of moles of oxygen multiplied by Ru. There is a universal gas constant multiplied by temperature of oxygen divided by the pressure of oxygen. So let us put in the value. So 0.219 multiplied by 8.314 multiplied by 313 divided by 100. So this value comes out to be
Battery is
5.70.
charging.
meter cube, and the volume of the nitrogen gas, that is n number of moles of nitrogen multiplied by the universal gas constant multiplied by the temperature of nitrogen and the pressure of nitrogen. So these were the initial volumes. So 150. So this comes out to be 2.32 meter. Now, since the tank is rigid, after mixing, the final volume will be the sum of the individual volumes of the components. After mixing, the final volume of mixture volume of nitrogen plus the volume of oxygen. Okay, this is 2.32 plus 5.70, that is 8.02 meter cube. This is true because the container is rigid. Since the container is rigid, okay, therefore the final pressure of the mixture we are we are doing this under the assumption that the mixture of two ideal gases will also be an ideal gas. Okay, since both the gases that are mixing are ideal gases, so we are considering their mixture to be also an ideal gas. So we are using the ideal gas equation for the mixture as well. So the this final pressure of the mixture is equal to the number of moles in the mixture multiplied by the over universal gas constant multiplied by the temperature of the mixture and the volume of the mixture. So the number of moles of the mixture we have determined it to be uh, 0.362. 0.362. This is multiplied by 8.314. And what is Tm? The mixture temperature is 305.2 Kelvin. And the final volume of the mixture is 8.02. Okay, this one is in kilojoule. So we will get the pressure to be 114.5 kilopascal. From this kilojoule we are getting this kilopascal. Okay, so this is the final pressure of the mixture. So I hope this analysis is clear to everybody. If there is any doubt, you can ask. So if there is a doubt, please do ask, else we will move on to the next problem. Okay, so I am taking that there is no doubt. Now we will move on to another problem, uh, like where we'll be using the mixture of gases and employing the concept of entropy. Okay, so let us start with this problem. Okay, so an insulated rigid tank is divided into two compartments by a partition. One compartment contains 3 kilomole of oxygen and the other compartment contains 5 kilomole of carbon dioxide. Now both the gases are initially at 25 degrees Celsius and 300 kilopascal. Now the partition is removed and the two gases are allowed to mix. Assuming the surroundings are at 25 degrees Celsius and that both the gases behave as an ideal gas, as ideal gases, determine the entropy change and the decrease in the available energy associated with this process. Okay, so let us first try to understand what the process is happening in this case. So this is a rigid tank. Okay, okay, so this is a rigid tank. The on one side of the partition there is oxygen gas of 3 kilomole and 25 degrees Celsius and 200 kPa, and the other one is carbon dioxide at 5 kilomole, 25 degrees Celsius and 200 kPa. Okay, so both the gases are at same temperature. Since there is no mass that is crossing the boundary, let us assume this. Let us perform this analysis as a closed system analysis. Okay, so we are considering this as the system. Okay, so this is the system. So this is a closed system. So this is a closed system, and the ambient is at 25 degrees Celsius. Okay, now there is mixing of the two gases, and finally uh, so finally uh, so this is a mixture, or let Tm be the temperature of the mixture and Pm be the pressure of the mixture. Okay, and the surrounding is still at 25 degrees Celsius and the system remains the same. This is a closed system. Okay, so this is a problem. So a rigid tank with this mix gases are now the partition, after the partition is removed, there is a mixing of the gases, and the entire process occurs in a closed system. Okay, now what is the analysis here? See, since both the gases are at 25 degrees Celsius and 200 kilopascal, that is, they are at the same temperature and pressure, and we are assuming that there is no heat transfer from this system. There is no heat transfer from this system. Okay, since it is a rigid body, and that is, and we are assuming that while the partition is removed, there is very minimal work done on the system. So, and for a rigid system, there will be no other displacement work. And if we assume that there is no heat transfer to the system, then we can consider that uh, uh, finally the mixture will be at the same temperature and pressure. Okay, because there is no other heat interaction. So ultimately the internal energy will remain the same, because for this closed system there is no heat transfer, there is no work done, so the internal energy will remain the same. Okay, so since internal energy remains the same, so the temperature will remain the same, and as such since no other expansion process has happened, because of the volume being constant, it being a rigid container, so the pressure will also remain the same. That is, the pressure of the mixture will be equal to the pressure of the individual components, and the temperature of the mixture will be equal to the temperature of the individual components. So just let me write this down. uh, since both the gases are at 25 degrees Celsius and 200 kPa initially, assuming that there is no heat transfer, heat transfer to or from the system, and since the volume is rigid, since the volume is constant, rigid tank, a constant volume implies that there will be no displacement work. We are also neglecting any work that was done by removing of the partition. So in that case, the final temperature and pressure of the mixture will be the same. Will be 25 degrees Celsius and 200 kPa. Okay. Since as I have already explained before, so this the temperature and pressure of the mixture will be equal to the temperature and pressure of the individual components. Now, what is the change in entropy of the system due to mixing? Let us call it as delta S of the mixture, that is equal to sum of the product of the number of moles of each component and the change in the specific molar entropy of the individual component, that is delta Si bar. Okay, where delta Si bar is the delta Si bar is equal to the specific molar entropy change of the individual component. Okay, so um, okay, so how will we go about it? So this is the NO2. And for considering oxygen and nitrogen as ideal gas, so we can write the entropy change, the specific molar entropy change in terms of the for an ideal gas we can write it as this for in this form Cp ln of Tm. This is the mixture final mixture temperature by TO2, where this value denotes the initial temperature of the mixture, initial temperature of the oxygen gas, minus R universal ln. This is a universal gas constant, and this is Pm by PO2. Okay, and this is N nitrogen, Cp ln Tm by T nitrogen minus R universal ln of Pm by P nitrogen. Okay, so this is again T in nitrogen and P nitrogen are the temperature and pressure of nitrogen before mixing. Okay, now we have since this Tm is equal to TO2 is equal to Tn2. Okay, this will be mm, not P. This is not a total pressure of the mixture. This is actually the partial pressure of oxygen in the mixture. So this is PmO2. Let me write it as O2, and this is PmN2. So this is the partial pressure of nitrogen in the mixture. The temperature of the mixture Tm is equal to the temperature of the individual components, right? So this is Tm by TO2. This will be 1, and ln1 will be 0. Similarly, ln this one will be 0. So this term gets cancelled. Okay, so delta S mixture becomes minus R universal NO2 ln of PmO2 by PO2. Now, and also this total pressure of the mixture will be equal to the pressure of the individual component. So, this PO2 can be written as Pm. Okay, this is the partial pressure of oxygen in the mixture. This is the total pressure of the mixture. And sorry, let me write it as in subscript. This is the number of moles of oxygen, and this is the number of moles of nitrogen. This is ln partial pressure of nitrogen in the mixture by the total pressure of the mixture. But this value is partial pressure of oxygen in the mixture by the total pressure of the mixture, that is actually the mole fraction of oxygen in the mixture by Dalton's law. Okay, so is equal to the mole fraction of oxygen. Okay, and the partial pressure of nitrogen in the mixture by the total pressure of the mixture will be equal to the mole fraction of nitrogen. Okay, therefore this delta S mixture can be written as the universal gas constant, number of moles of oxygen ln of Y of oxygen, plus number of moles of nitrogen ln of Y of nitrogen. Okay, now the number of moles of oxygen is 3 kilomole, and the number of moles of nitrogen is 5 kilomole. Okay, so the total number of moles in the mixture is 8 kilomole. Therefore, the mole fraction of nitrogen is 3 by 8, that is 0.375. Okay, and the mole fraction of uh, sorry, this is the mole fraction of oxygen. This is the mole fraction of nitrogen. This is 5 by 8, 0.625. Okay, therefore delta S mixture is minus 8.314. This is in kilojoule per kilomole Kelvin. Yeah, this is in kilojoule per kilomole Kelvin. This is in kilomole. This will come in kilomole. So it will ultimately come in kilojoule per Kelvin. So 3 multiplied by ln of 0.375 plus 5 ln of 0.625. Okay, so this comes out to be 44.0 kilojoule per Kelvin. So the entropy change of the mixture due to the mixing process is 44.0 kilojoule per Kelvin. Okay, then what else do we have to determine? We have to determine the decrease in the available energy associated with this process. So the decrease in available energy is basically given by a theorem called the Gauss-Todula theorem, which links the exergy or the loss in the available energy with the entropy generation term for a process, or the net change in the entropy of the universe. It is said that the decrease in the available energy of a system is proportional to the entropy that is generated in the system during a process. Okay, and this proportionality constant is the temperature of the surrounding. So from the Gauss-Todula theorem, we can write the decrease in the available energy is T naught to delta S universe, or equivalently this is entropy generation of the system. So this is by Gauss-Todula theorem. Uh, now for a closed system with no heat or work interaction with the surroundings, we have assumed that there is no heat and work interaction. Uh, the change in entropy of the universe, that is entropy generation term, will be equal to change in entropy of the system itself, like it is an isolated system. Closed system, that is there is no mass interaction, there is no heat and work interaction, so it is like in form of a isolated system. So that will be equal to delta S of the mixture, and that is we have found out to be 44.0 kilojoule per Kelvin. Okay, so this one is 298. The ambient temperature was given as 25 degrees Celsius, that is 298 Kelvin. Okay, so 298 multiplied by 44.0 kilojoule per Kelvin, and this is in Kelvin. Okay, so it will come out to be 13112 kilojoule, or 13.11 megajoule. So you can see from this that the due to just a mixing of the two gases, there is so much loss of energy in order of megajoule, that is 10 to the power 6 joule. Okay, so this decrease in available energy is very high, which implies that these mixing processes are very irreversible. That is, they are any kind of mixing process is a very highly irreversible process. From this theorem, we can also say that since the entropy delta S of the universe is always increasing, that is delta S of the universe is always positive, it is greater than equal to 0. Equal to 0 for a reversible process, it is greater than 0 for any real process. Okay, so the decrease, that is the available energy, is always decreasing, because the decrease is a positive term. Okay, so the available energy is always of a isolated system will always decrease. This is like the energy of the universe is constant, the entropy of the universe is always increasing and the available energy of the universe is always decreasing. That we can infer from this. Okay, that is whatever a system was and whatever energy a system was possessing at any point of time, if it undergoes any kind of process in any kind of real process, it will always the net available energy of the universe, that is the system and the entire surrounding that the system is interacting with, it will always decrease. Okay, so just as an inference, let me write that since this is very high, we can write that the mixing process is highly irreversible. Okay, so I hope this is clear to everybody. If there is any doubt, you can ask. Else, I will move on to the next problem. Okay, so I guess that there is no doubt. So let me move on to the next problem. Here we will be utilizing the concept of the mixture mm, uh, and using it for a process wherein the mixture is flowing through a nozzle. Okay, so in the basic application of the steady flow energy equation, we have studied how uh, mm, like a single substance, that is, or a pure substance, how if it is moving through a nozzle, what happens. Okay, so here we were using it for a mixture. So a gas mixture consisting of carbon dioxide and oxygen with mole fractions of 0.8 and 0.2 respectively expands isentropically and at steady state through a nozzle from 700 Kelvin 5 atmosphere 3 meter per second to an exit pressure of 1 atmosphere. Determine the temperature at the nozzle exit, the entropy changes of carbon dioxide and oxygen from the inlet to the exit, and the exit velocity in meter per second. Okay, so this is basically the nozzle, and the mixture of carbon dioxide and oxygen, it is entering a 700 Kelvin 5 atmosphere and 3 meter per second. It undergoes an isentropic expansion process wherein the pressure decreases from 5 atmosphere to 1 atmosphere. Okay, in this process we have to determine what is the final temperature of the mixture at the exit, that is the temperature at exit, the exit velocity, and what is the entropy change associated with the process. Now it is we have entropy change of the individual components. Okay, now we have been said that the process is isentropic, that is the expansion process is isentropic, that is for the entire mixture there is no entropy change. However, for the individual components, as it moves through the nozzle, there will be entropy change, and we have to determine that as well. So, for the mixture in total, for isentropic expansion, okay, the specific molar specific entropy of the at the two states will be same, that is there will be no change in the entropy. So that is where 1 and 2 are initial and final states of the mixture. That is, this is the state point 1 and this is the state point 2. Okay. So since there is no change in the entropy, then it becomes 0. So we can say that this term can be written as the mole fraction of carbon dioxide multiplied by the change in the specific entropy of carbon dioxide from inlet to exit, plus the mole fraction of oxygen multiplied by the change in the specific entropy of oxygen from the inlet to exit, that is 0. Okay. Now this term can be written as YO2, let's say YO2, this is SO2, S not O2, that is this value at temperature T2 minus this value at temperature T1. So first, what are these values? These are the ideal gas property values of oxygen corresponding to the temperature. Like at 0 Kelvin, we consider the entropy of the substance of any these of all of these gases to be 0. So if there is only a change in the temperature without any change in the pressure, then as the temperature changes from 0 Kelvin to a value of T2, that is here it is we don't know, T1 we know to be 700 Kelvin. So as the temperature changes from 0 Kelvin to a particular temperature, what will be the entropy of that ideal gas with respect to its value at 0 Kelvin, which is again 0. Okay. So this is the value S naught uh, S naught 2 I'm sorry, S naught of oxygen and bar, because we are considering the entire analysis on a molar basis. Okay. So this value can be determined from the any ideal gas property chart for oxygen, and similarly for carbon dioxide, and this was due to the variation in pressure, this was due to the variation in temperature. What is the change in the entropy? Now for the change in the pressure, we have to write it as R ln of P2 by P1, where P2 is the final pressure and P1 is the initial pressure. Okay, plus YCO2, same things for CO2, S CO2 at temperature T2 minus SCO2 at temperature T1 minus R ln of P2 by P1. This value for CO2. Okay, this is ultimately again the sum of these is 0. So YO2 SO2 not bar at T2 plus YCO2 SCO2 not bar at T2 is equal to R. We are taking this one on the right hand side. So this is YO2 plus YCO2. Okay, R bar ln of P2 by P1. This is the sum of the mole fraction, so this has to be 1, plus this one YO2 SO2 not bar at T1 plus YCO2 S not bar of CO2 at T1. Since we know T1, that is T1 is 700 Kelvin, and so we can determine these values from the ideal gas property of oxygen and carbon dioxide. Okay, so using these values we can determine, if we put in these values of the mole fractions, then we can determine it to be 0.2 SO2 naught bar at T2 plus 0.8 SCO2 naught bar at T2 this is equal to 0.2 multiplied by 231.358. So this value has been found to be 231.358, and this value has been found to be 250.663 plus 0.8 into 250.663 plus 1 into 8.314 ln of what is the pressure. Final pressure is 1 atmosphere and the initial pressure is 5 atmosphere, so this will be 1 by 5. Okay, so as such we can write this 0.2 s not s oxygen not bar at T2 plus 0.8 s carbon dioxide not bar at T2. The value comes out to be 233.42, but we don't know the value of T2. So how will we do it? We use an iterative approach now. So using an iterative approach for T2 at an initial gas of 510 Kelvin, at T2 is 510 Kelvin, this value from equation 1, if we at 510 Kelvin, if we calculate these values, the entropy values corresponding to oxygen and carbon dioxide, and put it in equation 1, we will get it as 0.2 multiplied by 221.206 plus 0.8 into 235.700. This is equal to 232.80. This is less than the value on the right hand side. So again at T2 of 520 Kelvin, sorry, so equation 1 again implies, so at 520 Kelvin, if we put if we calculate these entropy values, we'll get this value to be 221.812 plus 0.8 into 236.575. So this comes out to be 233.60. So this value is again more than this one. So now we will perform an interpolation between these two values. Okay, so by linear interpolation, you can write T2 minus 510 by 520 minus 510, and corresponding to T2, what was the value on the right hand side? It was 233.42, minus for 510 it was 232.80, and for 520 it was 233.60, and for 510 it was again 232.80. So on solving, the value of T2 comes out to be 517.6 Kelvin. So this was the temperature at the nozzle exit. Therefore this is the temperature at the nozzle exit. 517.6 Kelvin. Okay, now from inlet to exit, if we see the individual gases, if we consider the gases individually, then from inlet to exit, okay, delta S of oxygen, molar entropy change of oxygen is S oxygen bar at T2 minus S oxygen not bar at T1 minus R ln of P2 by P1. So this is 221.667 minus 231.358 minus 8.314 ln of 1 by 5, and this comes out to be 3.69 kilojoule per kilomole Kelvin. And delta S of carbon dioxide, specific molar entropy change of carbon dioxide, is S carbon dioxide not bar at T2 minus S carbon dioxide not bar at P1 minus R ln of P2 by P1. This will be, these are also universal gas constants. Okay, so this is 236.635 minus 250.663 minus 8.314 ln of 1 by 5. Okay, so this is minus 0.92 kilojoule per kilomole Kelvin. Okay, so these are the entropy changes associated with the individual gases. Now finally, for the control volume, it was stated that the process is at steady state. So for the control volume at steady state, the change in energy of the control volume will be 0. So here there is no heat input to the control volume, there is no work done by the control volume, there is no change in the potential energy. Okay, so the energy equation reduces to h1 minus h2 plus v1 square minus v2 square by 2. This implies the final velocity will be equal to v1 square plus twice of h1 minus h2. Okay, now h1 minus h2 will be equal to h1 bar minus h2 bar by m, where m is equal to the molecular weight of the mixture. Okay, and these are the specific molar entropies, specific molar enthalpy change. Okay, the molecular mass of the gas is 0.8 into 44 plus 0.2 into 32. 0.2 is the mole fraction of oxygen, hence 0.2 multiplied by 32. 0.8 is mole fraction of carbon dioxide, so 0.8 multiplied by 44, and it comes out to be 41.6 kilojoule per kilomole. Okay, and this value, h1 bar minus h2 bar by m is equal to 1 by m multiplied by h1 minus h2 bar will be y of oxygen, h1 bar minus h2 bar for oxygen plus y of carbon dioxide, h1 bar minus h2 bar for carbon dioxide. Okay, these values h1 bar and h2 bar for these carbon dioxide and oxygen are similarly as we determine the entropy values, we can determine these h1 bar values and h2 bar values from the ideal gas property table for oxygen and carbon dioxide. So this is 1 by 41.6, this is 0.8 multiplied by 211.21184 minus this is 15320 plus 0.8 into 27125 minus 18468. Okay, so this value comes out to be 194.7 kilojoule per kg. Okay, therefore the velocity will be 3 square, that is initial velocity was 3 plus 2 multiplied by 194.7, this is a kilojoule, so 10 to the power 3 in joule. So the velocity comes out to be 624 meter per second, which is the exit velocity. So the exit velocity is 624 meter per second, which is so high as compared to 3 meter per second, which was the inlet velocity. That is, the enthalpy is now getting converted to velocity, as we have seen previously, but here the properties are of a mixture. I hope this is clear to everybody. If it is clear, then I will move on to small problems related to psychrometry, and that is a mixture of air and water vapor. That is like gas and vapor mixtures problems. Okay, so if there is no doubt, then I will move on to this problem. So a 5 meter, 5 meter, 3 meter room contains air at 25 degrees Celsius and 100 kilopascal at a relative humidity of 75%. Determine the partial pressure of dry air, the specific humidity, the enthalpy per unit mass of dry air, and the masses of dry air and water vapor in the room. So this for this, we are assuming that dry air and water vapor are ideal gases. Okay. Now for water at 25 degrees Celsius, the saturation pressure is 3.1698 kPa, and the enthalpy of the vapor phase at the saturation temperature of 25 degrees Celsius is 2546.5 kilojoule per kg. Now, relative humidity, we know relative humidity phi is the ratio of the partial pressure of vapor in the mixture divided by the pressure of air at which it becomes saturated corresponding to that temperature, that is the pressure corresponding to the saturation pressure corresponding to the temperature of 25 degrees Celsius, or that any particular fixed temperature. Okay, so this implies the PV value will be equal to phi multiplied by saturation temperature at 25 degrees Celsius. Okay, so this is equal to 0.75 multiplied by 3.1698, and that is 2.38 kPa. Okay, so this is the partial pressure of vapor in the mixture. Therefore, the partial pressure of dry air is the total pressure minus the partial pressure of vapor. So the total pressure is 100 kPa and the partial pressure of vapor is 2.38. So it comes out to be 97.62 kPa. Now the specific humidity. The specific humidity is the ratio of the mass of water vapor present in unit mass of dry air. Okay, so like the mass of vapor per unit mass of dry air. Okay, this if we simplify, we will get it in terms of partial pressure of vapor as 0.622 PV by P minus PV. So if we put in the values, and this is 97.62, so this comes out to be 0.0152 kg of water vapor. This is water vapor present in per kg of dry air. Okay, now the enthalpy per unit mass of dry air. So all these are actually expressed in terms of the mass of dry air. Okay, H is enthalpy of air plus W, that is W into HV. Why W? Because this is in mass of this HV will come in mass of the water vapor, per unit mass of water vapor, and if we multiply it with W, we will get it from this equation. From this equation, we will get it in terms of per unit mass of dry air. So the entire thing will be expressed in per unit mass of dry air. This is CPT plus WHG. Okay, so this is Cp is 1.005 and T, actually this is T minus 0, from 0 degrees Celsius we are calculating, so this is 25 degrees Celsius, that is 25 minus 0, and hence we are not, since it is basically a difference, we are not converting it to Kelvin. And this is 0.0152 multiplied by 2546.5 is Hg, corresponds to 25 degrees Celsius. Okay, so this comes out to be 63.8 kilojoule per kg of dry air. Now we have to determine what is the mass of uh, air and water vapor in the room. So both dry air and water vapor fill the room completely. Okay, so this is VA, is VV, is V room, and that is 553. 5 multiplied by 5 multiplied by 3, that is 75 meter cube. Okay, for dry air and water vapor as ideal gases. Okay, then the mass of air can be found out from the ideal gas equation PAVA by R A T A. So this is 97.62. This was the partial pressure of air multiplied by 75 is the volume. This is 0.287 and this is 298. So this comes out to be 85.61 kg. And mass of the vapor is PVVV by RVT. This is 2.38 multiplied by 75 divided by RV is 0.4615. So RV is basically 8.314 divided by 18 and this is 298. So this comes out to be 1.30 kg. So this is the answer. The masses of air and vapor in the room. Alternatively, the mass of water vapor can be found out as MV is can be also found from the specific humidity. So this is 0.0152 multiplied by 85.61 and it comes out to be same 1.30 kg. Okay, so I hope it is clear to everybody. Then if there is no doubt, then I will move on to the last problem for today. So an air water vapor mixture is contained in a rigid closed vessel with a volume of 35 meter cube at 1.5 bar, 120 degrees Celsius and relative humidity of 10%. Okay, so this is basically moist air. Okay, at 1.5 bar pressure, 120 degrees Celsius and relative humidity of 10%. Volume is 35 meter cube. It is cooled to a state, it still contains moist air at 22 degrees Celsius. Okay, if I show the process on a TV diagram, I can show it as like this. So this is one temperature and this is another temperature. So it starts at this point, it corresponds to T1 and this is PV1. It starts at this point and it moves as via constant volume line to reach this. Let this be 2 and this be 3. Okay, it moves via constant volume line. Okay, this is the point. The 2 is the point where condensation starts. Okay, so we have to first determine what is the dew point corresponding to the initial state. The initial state that is at 1.5 bar total pressure and 120 degrees Celsius. So the dew point is basically the saturation temperature corresponding to the partial pressure. So we have to first determine what is the partial pressure. Now the partial pressure of water vapor PV is phi multiplied by P total. This is P saturation at T1. So this is 0.1 multiplied by saturation pressure corresponding to T1. T1 is 120 degrees Celsius. Corresponding to that, the saturation temperature will be 1.985 bar. So that is equal to 0.1985 bar. So corresponding to this pressure, corresponding to PV is equal to 0.1985 bar, the saturation temperature is nearly equal to 60 degrees Celsius. Therefore, the dew point, which is equal to the saturation temperature corresponding to the partial pressure of vapor in a mixture, is equal to 60 degrees Celsius. Okay, so the initial state the dew point is 60 degrees Celsius. That is at initial, if it had moved by a constant pressure line, this temperature would have been 60 degrees Celsius. Okay, so if it had moved by a constant pressure line, then the condensation would have begun at 60 degrees Celsius. Okay, now but it doesn't move via a constant pressure line, it moves via a constant volume line. Now the specific volume of vapor at the specific volume of vapor at state 1 is VV1 is R universal T1 by MV V1. This is like the gas constant we have taken from the universal gas constant. So this is 8.314 multiplied by 393, and this we are dividing by the molar mass of water vapor, that is 18, and this is 0.1985 into 10 to the power 5, since this was in bar, so in Pascal. So this is 9.145 meter cube per kg. And since the it is a rigid tank, so the total mass of vapor will remain the same. Total mass of water will remain the same, the volume is the same, so the specific volume will remain the same. So the specific volume of vapor when condensation begins, that is VV at the state 2, will be equal to the specific volume of vapor at the state point 1. This is equal to 9.145 meter cube per kg, and this will also be equal to the specific volume of the gas phase corresponding to a saturation temperature of T2. Okay, if this is the at the temperature of T2, this is
Battery is discharging.
corresponding to T2. This is not 2, this is, let me write it as 3. Okay, so this is T2. So from the property table, corresponding to specific volume of the gas phase to be 9.145 meter cube per kg, we can find the saturation temperature to be 56 degrees Celsius. Therefore, condensation begins at 56 degrees Celsius. Okay. And the last part of the problem, that is what is the mass of the condensate. Okay, so the amount of condensate, to first we determine what is the initial mass of vapor. This is the total volume by the specific volume in the initial state. So this is 35 by 9.145, that is 3.827 kg. And finally, since the specific volume will remain the same, so we can write this as a fraction at this point. At the state point 3, the quality can be determined from VV3 minus VF by VG minus VF, and VF3 will be equal to VV3, it will be equal to VV1. So this is 9.145 minus 1.0022 into 10 to the power minus 3 divided by 51.447 minus 1.0022 into 10 to the power minus 3. So this value comes out to be 0.178. Okay, therefore the final mass of vapor will be equal to, so initially this was present, and now after the condensation began, from this mass a fraction has converted to water and the remaining fraction is in vapor, and this is the fraction that remains in vapor. Fraction of what? Fraction of the total initial mass of the vapor. So this is 0.178 multiplied by 3.827. This comes out to be 0.681 kg. Therefore, the amount of condensate is mv1 minus mv2, that is equal to 3.827 minus 0.681, and that is 3.146 kg. Okay, so the problem is solved. I hope this is clear to everybody. If there is any doubt, you can ask, else we will end today's session. Okay, so I am taking that there is no doubt. So let us end today's session. I thank everyone for joining, and I request all of you to join the next session next Friday from 6 to 8 p.m. and make this our teacher success. Thank you. Please join. Thank you.